Good evening all. The last session for the session, let me share my screen. Welcome to the last session on fundamentals of convective heat transfer course for this particular year. So this week, this last session especially aims to give a brief overview of whatever we have discussed throughout in this particular lecture. I will only focus on some of the main points, and yeah, we will not be discussing any problems in this session. This is aimed to kind of give you a summary of whatever is covered in the lecture videos. We started out with in the introduction part of it, we started out with various kinds of flows, and then we completed week one with the incompressible flow equations, followed by an for continuity mass balance, momentum balance, and energy balance. Subsequently, we important discuss something which is mostly important is the boundary flow equations, and we'll just go one by one. So the first part is on the incompressible flow equations, where the incompressibility is essentially what that means is the flow velocity is less than the speed of sound in that particular medium, which amounts to giving this particular equation that the divergence of velocity vector is zero. And similarly, the Navier-Stokes equations, further on subsequent assumptions, we eventually came to these Navier-Stokes equations, where we have different terms for the unsteady part, the advection component, the pressure gradient component, the buoyancy or the gravitation component, and followed by, it's the gravitation component followed by the viscous components. This is again for the specific case of incompressible flow, unsteady Newtonian constant properties fluid. Like for all these assumptions taken together, we derive the equation for momentum, and finally, for deriving the energy equation, we invoke the Reynolds transport theorem, which essentially says that the total change in property material derivative for the system will be what the rate of change within the city plus whatever is crossing the boundaries. And this is the boundary term where the integral will be like if you evaluate the integral for the outlet, this will be positive, and for the inlet, that will be negative. And using this integral property, using this Reynolds transport theorem, we have taken a control volume and applied the energy balance, giving us this equation. The rho Cp dt by dt is the material energy change is given by Q triple prime is the volumetric regeneration term, plus this is the conduction term, plus these two terms will actually be present in case of compressible flows or where the velocity of the flow is significantly higher. In that we have the viscous dissipation term, and this term can actually be neglected in our cases. Like this will be true when you have like for gases, this will actually go off. And then the next most important one is the boundary layer flow. When you have a surface and on which if flow is happening, then you have very close to the surface, the velocity will be zero, and far from the surface, the velocity will be equivalent to u infinite. So as how the velocity varies from zero to this is governed by this boundary layer flow. So from the equations which we started out previously, from these equations, we'll apply each of the simplifications. So we'll apply something called scaling analysis, in which the continuity remains the same. However, after since this is a flat plate, the pressure gradient term goes off, and we'll also neglect the other terms. Eventually, we'll end up with this equation, which has the in the viscosity term along the x direction the velocity gradient is small, so that will be neglected, and this is equation. So here we have two equations, and we are essentially left with the two unknowns u and v as a function of x comma y. But of course, these are partial differential equations which cannot be solved directly. So there are other techniques to solve these equations which we'll look later. But just very similar to how we have the velocity bound layer, similarly, if the temperature of the fluid is not equal to the temperature of the surface, then we'll be having the thermal boundary layer. And for that, we'll have temperature varying from T infinity to TW or whatever is surface. And this is drawn assuming wall temperature is higher than the free stream temperature. So we'll have very similar equation as follows. Like here, this will be nu, here it will be alpha, and the non-dimensional number that defines how these two profiles are related to each other will be the Prandtl number. So delta by delta t is going to be a function of the Prandtl number. So after applying scaling analysis, we have different cases where the thermal boundary layer thickness is less than delta, then Nusselt number will scale as Prandtl to the power 1 by 3. However, for delta t greater than delta, this will be scaling as Prandtl to the power 1 by half. When will this and this will happen? Yeah, this is for liquid metals where you have delta T very high greater than delta, for which Prandtl number is very much greater than 1. This is going to happen. However, for ordinary gases, delta T will be less than delta or for like close to delta, and it will also scale as 1 Prandtl to the power 1 by 3. For say oils or something, also it will scale in this particular fashion. So as I said before, the partial differential equations are hard to solve. So we have to come up with some hypothesis to reduce these equations into ODEs, which we can solve with the existing techniques. The idea that is used is something called a similarity theory, where we assume that the velocity profile at two different points are very similar to each other, are similar to each other, so that u by u infinity is only a function of some similarity variable eta, which will be y by delta. And with that assumption, we just solve the solution and we obtain the skin friction coefficient equations as follows. Similarly, for the thermal boundary layer, assuming again delta T is more or less equal to delta or delta T less than delta, we got the values for Nusselt number. And then comes the Kolb's analogy, which relates this is the Stanton number, which is defined as Nusselt number times Reynolds number by Prandtl number is equal to CFX by 2. So what this tells us is if I know the skin friction coefficient for a particular flow and Prandtl number, then I can calculate the Stanton number, and from Stanton number I can compute my Nusselt number, from which I can get the heat transfer. And of course, this is for constant wall temperature. When we have a uniform heat flux, then the temperature of the surface will not be constant. Instead, it will be varying as C to C square root of x. And then next comes the two important concepts of displacement thickness and momentum thickness. As we know before, that if you have a boundary layer, if I have a boundary layer, because of the presence of this wall here, if I make a complete rectangular one, then there is so much mass influx, but the equal amount of mass is not actually going out. And you have some outflux on the top. So the difference between this, the mass deficit, is given by this displacement thickness. What that means is how much should I actually go upwards so that the net mass in will be equal to net mass out. So that rho infinity times delta star will be the mass deficit that is happening because of the presence of boundary layer. Similarly, whatever is the momentum deficit is given by theta, or the momentum thickness, so that when you multiply rho infinity square times theta, that will give you the momentum deficit. These two are important definitions, which are again used in approximate solutions. So the previous exact solutions, we actually ended up with ordinary differential equations, which have to be solved using numerical techniques. So the alternate way to solve the same thing is using approximate solutions, wherein we take the original equations, integrate them, and come up with something called integral form of the governing equations. Then we assume a profile for the solution, so that the entire equations, like we have only one equation, that will be either the momentum integral or the energy integral equations. So since we have one equation, we can only solve for one unknown. So we will assume a profile, and that profile should satisfy the boundary conditions, like at the wall the velocity should be 0, at y equal to delta the velocity should be equal to. So the boundary conditions are typically like at the wall we have velocity to be 0, at infinity velocity should be equal to u infinity or t equal to t infinity, and then we have the condition that at close to the wall we have u equals to 0 and v equals to 0, so both of these terms will go to 0, so we'll be end up with del square u del y square at y equal to 0 equals to 0. Similarly, at the free stream we need to have 0 shear stress. That keeping all these conditions, we can determine the constants and come up with a polynomial equation for the u, the similarity velocity, that is u by u infinity, the non-dimensional velocity. Once we have the velocity profile, the only unknown is going to be delta. So we will substitute this equation back into the integral form and then solve for that delta. Once I have delta, I can use that equation and solve the energy equation, get delta T. This is the integral form. So these are the equations that needs to be remembered, where the tau w by rho infinity square, this is basically my skin friction coefficient, half of the skin friction coefficient is given by the derivative of the momentum thickness. Similarly, for the energy equation, we have the term as follows. However, the main thing to note here is the solutions here, like assuming QB profile, are close to the exact solutions that we obtain. But as we discussed even before, that these solutions are not accurate in any form. And even though, for example, you assume the profile, you got a solution, and if they are not matching with experiments, you do not know how to improve them directly. So that is not a straightforward way. But still, this gives you reasonably accurate solutions, like you assume a profile that gives you the velocity profile, it gives you the Nusselt number, it can give you skin friction coefficient, and all these values can easily determine without having to go through the long transformations that we will be doing in the Blaise solution. These are all external flows. Next comes the internal flows we discussed. As the internal flow is where you have the fluid will be surrounded by walls or something. Usually the two different regimes are there. So either you have a fully developed region or a developing region. During the initial region of the flow is called a developing region, where the two boundary layers are not matching with each other. And then we have a developing region. In the developing region, we'll be having in the fully developed flow, the Nusselt number will be constant. The boundary layers have actually merged with each other, and we have a uniform velocity profile. Like the velocity profile equations, again, we have different regions. Like you can have a parallel plate channel flow, or you can have a circular pipe, the Hagen-Poiseuille flow. There are all these derivations we have already gone through in the weeks. The key criteria is the Nusselt number is a constant value. So unlike the previous case, as an external flow, Nusselt number is actually a function of the local Reynolds number. So if you see the Nusselt number relation here, it is going to be a function of local Reynolds number. But interestingly, even here, it is going to depend on the value of x per developing flow. But once the flow has fully developed into the fully developed region where both the boundary layers have merged with each other, then the Nusselt number is going to be constant, and it will not be varying as a function of as in the axial direction. That is exactly the definition of fully developed flow. But here again, the walls can have two different types of boundary conditions. Either it can be uniform wall temperature or uniform wall heat flux. In here we have different cases, as in for the developing flow, either it's similar to here, we have parallel plate circular pipe, and then we also have the quad flow case where the one of the plates, the top plates, is actually moving relative to the bottom plate. So there is instead of having the zero velocity on both top and bottom, one of the plate is actually moving. So you have a finite velocity on the top. Then you have different Nusselt number on both top and bottom plates. Depending on, again, here you can have two possible combinations. You can have both the walls to be isothermal, or one of them isothermal and the other one being adiabatic, giving two different values of it. So when one of them is adiabatic, the question of Nusselt number does not exist because Q equals to 0. Nusselt number will not be, there is no point in defining Nusselt number over there. The only thing that is interesting there is finding the temperature. So all these two equations are relevant when the velocities are actually high, and we came up with a new number called Eckert number, which will give us an estimate of how much energy is getting transported, the kinetic energy to the heat energy. So if the Eckert number is higher, then it means that, especially true when you have higher Mach numbers, this Eckert number is again related with the Mach number of the flow. For low Mach number of flows, this number is actually close to 0, so we can neglect this. Otherwise, it will be actually be high. When for high velocity flows, this is significant. So how we get, in order to even get these relations, we have to include the viscous dissipation term into our energy equation. In the first, like a few slides before, I have showed the viscous dissipation term that has to be accounted for. Otherwise, you would not end up getting these terms at all. And both of these external flow, like the previous one for the boundary layer flow, or even in this internal flows, the common thing in both of these flows is that we have an external driving agent. So in the previous case, there is a free stream velocity u infinity, which is maintained because of there is some pressure gradient externally. Or similarly, in case of internal flows, even in Hagen-Poiseuille flow or parallel plate flow, there is an external pressure gradient that is being maintained. But for example, when you have a co-ed flow, there is a top plate that is moving with a constant velocity, which is again an external means that is imposing this thing, which are all the forces that are happening at the boundaries. There is no body force term that is involved. The next one is an external flows, is where you have the body force or the buoyancy or something of that sort that is actually driving the flow. However, in reality, we will have both of these together, so we need to understand when to use which, and that is where the Richardson number will come into picture. It is defined as the ratio of Grashof to Reynolds number square, where Grashof will signify the strength of buoyancy driven flow, and Reynolds number will give you the strength of post convection. So if Richardson number is close to 1, you can consider that to be mixed convection. If it is very much greater than 1, then it is natural, and very much less than 1, it is a post convection. And we have different scaling laws. These are important for natural convection design. So all these are for natural convection. When Prandtl number is very much greater than 1, delta T will scale as RH to the power minus 1 by 4. And if it is very much less than 1, it will scale as Prandtl to the power minus 4 NH into Rayleigh number to the power minus 1 by 4. Wall to peak velocity, thickness of wall jet, and velocity scale are other important parameters. Where wall to velocity peak is like when you have a natural convection, the velocity would actually when you are having natural convection over, say, the vertical plate, close to the wall it will be 0, and far downstream it will be 0. So it has to reach a maximum velocity and then it should go to 0. So this versus this peak is given by this, and the thickness of the wall jet, the thickness is given by the other expression, and velocity will be scaling at RH to the power half. So knowing this, again, Nusselt number is RH to the power 1 by 4, and if it Prandtl number is very much less than 1, then Prandtl number should also be taken into account. And these are different correlations. As we have been discussing before, whenever you look at a correlation, important things are what the entire heat transfer is characterized by only one non-dimensional number in case of vertical plates, which is the Rayleigh number. And depending on the range of Rayleigh numbers, they have different correlations, because for each range you have a different regime. So for example, in 10 power 4, 10 power 9, it will be in the laminar regime. So you use the first correlation. And above 10 power 10, it will be in the fully turbulent regime, where you have the different correlation. And for the entire range, the last correlation is suggested by Church in June 1975 paper, where they have fitted for all the data that is available to them experimentally, and this is the correlation that is used. For inclined plane, you would actually use the same equation as if it was a vertical flat plate, just that the buoyancy force, the forcing term G, is replaced with G cos theta, where theta is the angle with the vertical. And the other one, the first one is an external natural convection, and this is an internal natural convectional flow, where you have two different walls, and both of them are at different temperatures. So if one of them is actually raising up, the air raises up, the other one it cools down, so there will be some circulation inside, but it won't be just one much circulation. As the temperature difference increases, the number of circulations internally will also keep increasing, and that is and from there they obtain the Nusselt number as a function of here h times delta T. When you apply, the delta T is the temperature difference Ph minus Pc, and based on that, these Nusselt numbers are defined, which will again depend on the Grashof number in this particular relation for different regimes, again, as I said previously. And the angle of inclination is given by the effect of these different correlations here. Up until previous one, we have been discussing only for the mostly for the laminar cases. Now comes for the turbulent cases, where the velocity will actually be function of time, but knowing that function is not straightforward. And the strategy that is being used is to divide the velocity and all other quantities that you measure into two components, a mean component and a fluctuation component. The fluctuating component is assumed to be random. So with that, we applied another technique called Reynolds averaging, or the time averaging, where we fix a time scale and then we integrate these quantities. So when you measure the velocity, it will be something like, so if I have experimentally measured the velocity, I'll get some profile. Say I got some profile like this. So what we are doing is fixing a time scale. Let's say this is a time scale, and I'm just integrating over the 10 time scale. This will give me the mean velocity, and once I have the mean velocity, actual minus the mean will give me the fluctuating component. So similarly, when this whatever is called this averaging, if you apply for all our governing equations, we would end up with these equations. The key idea here is, once you have these, we have additional terms coming into our Navier-Stokes equations, which are called the Reynolds stress terms. What these terms imply is this is also acting as if there is an additional viscosity that is present. However, since, as I said before, u prime, v prime, w prime, t prime, all these quantities are fluctuating or random components, which means we cannot directly get a value of them. So we need some closure to be able to solve these equations numerically. And that closure comes in different ways. One way is a Prandtl mixing length theory, which we have discussed previously, is you come up with a way to express these entire terms in a very similar way as this, just that you will replace mu with a different term called eddy viscosity that will relate the fluctuating component with the gradient of the mean velocity component. And then we come up with ways to estimate that mu t as a function of other velocity properties, and then there are several theories for that, which we are not going into in detail in this particular course. The key thing is, once we have this, the main quantities, the objective quantities that we are interested in is something called the turbulent kinetic energy, which is defined as half of u prime square plus v prime square plus w prime square. And again, we also have turbulent intensity defined in this particular way, which is RMS of these fluctuating components. And depending on the value of this turbulent intensity, we can classify it into either high, medium, low, or laminar turbulent flows, or either a laminar flow, which is again a straightforward one. Now we extend the theory to boundary layers. So similar to the laminar boundary layer, we have turbulent boundary layer. Equations are very similar to it. The only difference here is the quantity mu is now replaced with mu plus nu t. So there is an eddy viscosity term that is coming into the picture. And and the important thing to note here is this mu t, alpha t, whatever I'm writing here, are not functions of the are not properties of the fluid, but they are dependent on the flow properties. So if Rayleigh number is beyond a particular value, these values become significant. Otherwise, they tend to 0. And interestingly, we have something called universal velocity and universal temperature profiles. So very close to the walls, where the effects of this mu t can actually be like if you're very close to the wall, then the viscosity is actually way higher, and the flow properties are not dominant. It depends entirely on the fluid. We have the viscous subregion and then buffer region followed by fully turbulent region. Whereas in the fully turbulent region, the effect of molecular viscosity is negligible and only mu t will be dominating. And this is a mixing link theory. As I said before, there are other theories to get these equations. This is a universal turbulent velocity profile. The idea here is to come up with two new non-dimensional numbers. One is a y plus, which is the local Reynolds number, and u plus, which is the u bar related with u tau, where u tau is given by square root of tau w by rho. So what is the advantage with this particular profile is it says that this profile is independent of is universal in nature. So if you are solving for a particular flow, you do not have to solve everything. So there is certain regions which you can skip. And we have actually solved some problems during in say week I guess week 8 or 9. We actually solved a problem where we actually make use of this turbulent velocity profile to compute the velocity. So for example, we can use the integral equation, momentum integral equation, of course, for the velocity profile. The main challenge that we would be getting is we do not the profile that we eventually came up with is a one by power law, like 1 by 7 power law, where u by u infinity is y by delta to the power 1 by 7, and that obviously at y equal to 0, the tau will actually, the shear stress will actually tend to infinity with that particular equation. So we cannot close that equation directly. So we need to use this particular law, the universal turbulent velocity profile, wherein close to the wall, we'll actually, from this, we'll actually compute the CFX. Like we will have to know what the y plus value is. Like we are in this discuss up here in the fully turbulent region, and then we will use that corresponding equation. And from this equation, or for the entire flow, we can replace this with a power law equation. U plus is y plus to the power 1 by 7 times some constant. And from that equation, we will get the skin friction coefficient. Once we have the skin friction coefficient, we will substitute that back into our momentum integral equation, and from there we will be able to solve for boundary layer thickness and get everything else, the heat transfer coefficient, etc. Similar to the universal velocity profile, we have universal turbulent temperature profile as well. And this is the analogy that I have been mentioning about. The idea here is you have to express this u plus as a function of y plus. And once you have that at y equals to delta, u plus will be u plus u bar will be equal to infinity. So you can use that to get CF and substitute that here. Solve this equation for delta. Once I have delta, I can pre-compute, right, compute what is the value of CF, etc. And instead of solving for the energy integral equation, we can actually use the Kalpan analogy where Stanton number times matter to the power 2 by 3 CFx by 2. Whatever CF I'm getting here, I'll substitute that here, get the Stanton number. Once I have the Stanton number, I know the relation between Stanton number and Nusselt number as follows. I have to just take it on the right hand side, and that will give me the correlation for Nusselt number. We actually solved a problem for this. So if you want, you can go back to the lecture videos, or you can even see the live session, which is already uploaded on the YouTube for say week 9 or so. That will give you an idea of how to do this with an example problem. In the last week of the lecture videos, we discussed something on boiling, where we identified, like for the case of started out with the differences between evaporation and boiling, and then we identified something called pool boiling curve, where if the temperature of the heater is constantly increased, then the heat flux initially increases, reaches a maximum value, and then decreases, reaches a minimum value, and then keeps increasing. And then based on this gradients, we identify different regions, and each region will have a different heat transfer correlation to be used to calculate the heat flux, which is a main important point. So if you're in the first region for natural convection boiling, you have to use the natural convection correlations that we already used before for the differentially heated cavities, but just that the cavity is now vertical instead of the horizontal one that I have shown before. And next comes the nucleate boiling region, where the temperature difference or the excess temperature T1 minus T saturated is within say 5 to 30 Celsius, and followed by transition and followed by field one. Each one of them has different correlations. I've actually taken up problems in the nucleate boiling region yesterday, so you can go through week 12 example problems to actually get that, like to see an example of that. Uh, Subsequent to boiling, we have the condensation problem, where the again we can have either a dropwise or a film condensation. This is one particular example, or this particular derivation for all these values are pertaining only to vertical plate film condensation, where you have a water film or a liquid film falling only due to gravity forces. So the things here we will be interesting are what is the film thickness, what is the velocity, what is the condensation rate, net heat transfer rate. These will be the questions that we are interested in, and we have solved problems even on this one. And this is for a vertical plate. Similarly, we can also have a horizontal cylinder, which is the one that we usually see. And similar correlations can be obtained for condensation rate and the average heat transfer coefficient, which are similar to that, except for the coefficients are a little changed. Here, we actually solved a problem on this, and we compared the rate of condensation for both the horizontal tubes versus vertical cylinder. We also determined for what radius or what diameter of the horizontal tube the condensation rate will be same for this. And we also see how much percentage increase can be obtained if I change my cross section from round to flat, etc. All these problems were solved yesterday. And yeah, so these are all the things that we learned in this particular course. Thank you. Do you have any questions in particular that you want to discuss? So to quickly summarize as such, we started out with the generic equations, the Navier-Stokes and the incompressible flow equations, and then we extended it to energy equation. Once we got the energy equation, we again have different classes of flows, external, internal flows. We started out with external flows. We first solved the boundary layer equations. We observed that it is quite difficult to solve them directly, so we then used a hypothesis called similarity hypothesis, where the u by u infinity is only a function of some one variable instead of x comma y, it is only a function of y by delta. The delta is a function of x. With that simplification, we were able to get an ordinary differential equation, which we solved using different techniques, which is not covered in this particular course, but we discussed it in live sessions, which you can go where you can actually go through the YouTube videos for that, and got the solutions for Nusselt number, etc. Other than the numerical method, we have extensively discussed something called an approximate solution, which is an integral method. So the same governing equations are formulated in a different form, and then we solve for the boundary layer thickness, skin friction coefficient, Nusselt number, and all these values are obtained for external flows. Once we are done with external flows, we went into the internal flows, where we identified two different designs. That is a developing region followed by fully developed region, and the difference between these two is based on how the two boundary layers, how the boundary layers within the pipe or within the parallel plate are interacting with each other. If these boundary layers are interacting with each other completely, like they're completely mixed with each other, then it will be fully developed region. If they're very far from each other, then it is a developing region. And then we obtain the Nusselt number. Like first we solve the hydrodynamic case, where the fully developed velocity profiles are obtained for different cases, wherein you have two parallel plates, a channel flow or a circular pipe flow, which is a Hagen-Poisson flow. And then we gave temperatures to these walls so that the fluid temperature is different from the wall temperature. We solve the problem for both uniform wall temperature and uniform heat flux, and we obtain the Nusselt number correlations for these cases. And as I pointed out during the live sessions as well, there are two different things corresponding to the pressure difference here. One is the skin friction coefficient, which is because of the wall shear stress, and the other one is the fanning friction, which tells you the pressure gradient across the pipe or across the channel that you're going to have. And these two are different, and they're like if you take the wrong one, then you'd be off by more than 100 to 200%. So the key difference is the fanning friction is to essentially drive the flow, or which is opposes the flow at an ends, whereas the skin friction coefficient is to get the wall shear stress. Next, once we are done with internal flows, and we move on to external flows, where you have an external driving force. Again, here we also have external as well as internal, but the major difference is the forced convection versus natural convection. That's where the Richardson number came into picture, which tells us the magnitude of the Richardson number tells whether you are in forced or natural convection design. And within natural convection, again, we started out with the external flows, where you have vertical flat plate and natural convection over the plate. We solved again in different ways. We determined we used the same similarities theory and solved the equations. We also did using integral equation. Subsequently, we went to internal natural convection, where you have a differential heated cavity. However, we did not solve that problem directly, because it is quite difficult to solve analytically. So the solutions were presented in a numerical fashion, which I have not detailed here, but we actually discussed how to use the finite volume method to actually solve this problem. We have taken up some simple problems that we have already solved before, so that you get an idea of how to solve this. Subsequently, we moved on to turbulent flows, and we identified that velocity can be decomposed into two components. And in order to model this, we have used something called Reynolds average Navier-Stokes model. But then we found a problem there, that we have more unknowns and less equations. The concept of eddy viscosity has been introduced, but we understood that this eddy viscosity is not a molecular property, but it is a flow property, which means it is again dependent on the solution of the velocity, which is the thing that we do not know in the first place. And that's where we introduced other things. We made use of the mixing length hypothesis, mixing length theory, from which we were able to get an estimate of the steady viscosity in terms of the unknown that we are going to solve. That will be the additional equation. Once we solve that equation, we'll be able to solve our Navier-Stokes equations. And we discovered something called universal turbulent velocity and temperature profiles. With these profiles, we were able to use the integral solution and use Kalpan analogy. Both of them together, we were able to get the Nusselt number correlations. You can look up the problems that were discussed in week 9 and week 10 to actually solve these problems. Actually, in week 11 also, we actually solved a problem with this. Once we are done with external and internal flows, all of these are the temperature changes where there is no phase change. And the last one, the yesterday's lecture, is where we have discussed on phase change. We first initially started out with boiling, and we discussed only very specific to pool boiling case. We identified different designs, and each design, like the nasal convection, nucleate, transition, and film boilings, and each one has a different correlations, and each one of them is marked by the presence of the type of like the rate at which the bubbles are generated, and the interface between the solid and the liquid is where we were able to identify these different designs. And once we have the pool boiling, then the next thing that would come is the condensation. In the condensation, we limited our analysis to film condensation on vertical plate and horizontal tubes, arrays of horizontal tubes. All of these were discussed. We also discussed inclined plate, or where you just replace the g with the g cos theta or sin theta, depending on theta is with respect to vertical or horizontal. And that would be the end of our sessions. Yeah. So, are there any questions? Yeah, so that would be pretty much it. So I do not have any problems with this session. So this session is mainly aimed to give you just a connecting story to see what you have learned throughout the lecture. As I said before, so the main thing here is you will be either asked to find the heat transfer rate or you'll be asked to find the temperature. So all you'll be needing is the heat transfer coefficient. So this has been the main subject of interest in the entire lectures. So whatever you say, so either you are in a constant wall plate or uniform heat flux, uniform temperature, variable temperature, whatever it is the case, all we are interested in is finding this H. So in conduction, it is straightforward. Q is given by K times delta T by L, and K is a material property, so there was no problem. But once we move to, even in radiation, it would be property of surface, some surface properties times T power 4 minus T naught power 4. There also, once we know the temperature and material, we were able to do everything. But in convection, it is dependent on the material properties as well as on the flow properties. So we always were looking something to do, like we were always solving for the flow. So which is the case we did in the case of parallel plate. First we solved the velocity and then we got the temperature. These were all very, like in the post convection cases, the velocities were the only thing that we were able to solve, and then both the momentum and energy equations are decoupled from each other. So first we solve for the velocity, use that velocity in the energy equation, get the energy solution, get the temperature solution. Once we moved into natural convection flows, where buoyancy driven flows, the problem is that you have a temperature term in your momentum equation. So both the momentum and energy equations are coupled with each other. So all this, the way why we are dealing with all this is, once we have dealt with all of this, we came up with something called the heat transfer coefficient. And once I know the heat transfer coefficient, all I need to do is Q. If I know Q, to get temp, Q is equal to H times delta T. If I know temperature difference, I'll be able to calculate Q. If I know Q, I'll be able to calculate the temperature difference. So our entire aim is to get this heat transfer coefficient as a function of the geometry. So now this heat transfer coefficient in whatever case you see is given in terms of non-dimensional number, which is the Nusselt number. So all you'll be interested in looking up is, for your particular problem, if go to the literature, identify the Nusselt number, identify what the non-dimensional numbers are for your particular problem, get the corresponding correlation, look for the range of validity, and once you have the correlation, compute the heat transfer coefficient and get your heat transfer. So this is the main thing that is, like, from a problem point of view. Yeah. So I think we can end the session for today. There are no further questions. Yeah. I think there are no further questions. Thank you for joining and best of luck for your exams.